In this session, we are going to learn about k-means clustering, a fundamental and very practical algorithm in machine learning. It's especially powerful when you want to automatically find groups or patterns in your data without any prior labeling. Let's explore how it works and where it is used. K-means is an unsupervised machine learning method, meaning it doesn't require labels. It automatically finds patterns or groupings in the data by organizing points into k clusters. Each cluster is summarized by its centroid, the center of the group. The main goal is to minimize the distance between points and their cluster center. K-means is popular because it's simple to understand, fast to compute, and works even on huge datasets. It's extremely useful for tasks like customer segmentation, fraud detection, compressing images, and uncovering natural groupings in data. The k-means algorithm works through an iterative cycle. First, we choose the number of clusters, k. We randomly place k centroids. Then each data point is assigned to the nearest centroid. Centroids are then updated to the average position of their points. This process repeats until the centroids no longer move, meaning the clusters are stable. You can think of centroids like magnets. Data points are scattered to their nearest centroid. As centroids move and points reassign, clusters naturally tighten around their centers, creating clean groupings. This animation that I am going to play in just a minute illustrates how the k-means clustering algorithm works to identify natural groupings within data. We begin with a dataset of points scattered across two features, so feature 1 and feature 2. And these are all the data records, data points that we have in this data set. Disregard the colorings for now. So basically we have all these data points in data sets. The algorithm randomly selects initial centroids. So for example, it randomly selects 3 centroids as shown here as large black markers. So from there, each point is assigned to the nearest centroid. Let's say that all these data points in blue are assigned to this nearest centroid. Then these points in green are assigned to this nearest centroid, and similarly the points in red are assigned to this centroid. So it forms basically the temporary clusters, red, blue, and green groups in this figure. Next, the algorithm recalculates the centroid of each cluster by averaging the positions of all points within that cluster. So for example, let's say that it calculates the average of positions in this cluster and finds that the average is somewhere here. Similarly, it recalculates the average of positions in this cluster, and let's say that it finds somewhere here. Does the same thing and finds another centroid here. So the centroids basically move closer to the two centers of the data. By doing so, this moves closer to the center of the data. At this stage, some points may become closer to a different centroid than before. For example, these 3 points in green, they become closer to this centroid. And by doing so, they become part of this cluster. It may happen to some other points as well. So this reassignment is a normal part of the algorithm and continues until the cluster boundaries are stable. This process of assignment and centroid update repeats iteratively until the centroids stabilize and no longer shift significantly. The final result is a set of clusters where points within each cluster are more similar to each other than to the points in other clusters. So this demonstrates the power of k-means for uncovering patterns and structure in unlabeled dataset. So let me go ahead and play this animation. Before doing that, let me actually erase some of these boundaries so you can better see what's happening. Now let me play that and see how the centroids are created at the beginning. This is done randomly, and how the centroids are moving and new points are assigned to updated clusters. So for example, these 3 points that we have here, so initially they are part of this cluster because they are closer to this cluster here, but as we move the centroid, basically they become closer to this cluster and they become part of this cluster. So now the important question is how to choose the right number of clusters. Choosing the right number of clusters is crucial in k-means. If you pick too few clusters, you might miss important groupings in the data. If you pick too many, you can split natural groups unnecessarily and just end up fitting random noise. There are several methods to help. The first one is elbow method. In this method, you plot the total inertia, which is the sum of squared distances from each point to its centroid, against different values of k. So you look for the elbow where adding more clusters stops reducing the inertia significantly. This indicates that adding more clusters after this point doesn't improve the model much. The second technique is silhouette score. This measures how similar a point is to its own cluster compared to other clusters. A high silhouette score means the point is well matched to its cluster and poorly matched to neighboring clusters. You want to pick k that maximizes the average silhouette score. The other technique The third technique is Gap Statistic. This method compares the clustering you get from real data to what you would expect if your data were random. A large gap between the real and random scores suggests a meaningful clustering structure. And finally, domain knowledge. Don't forget common sense and context. Sometimes the correct number of groups is obvious from business needs or engineering requirements, even if the statistical scores are ambiguous. Often, it's best to combine multiple methods, start with elbow and silhouette, but confirm with domain expertise. On the left, you see inertia plotted against the number of clusters. Again, inertia is the total sum of squared distances between points and their centroids. As you increase k, inertia decreases. But notice the curve. Initially, adding more clusters sharply reduces the inertia. After a certain point, the elbow, adding more clusters doesn't help much. That elbow is often the best value for k. The silhouette score shown on the right gives another clue. It measures how similar a point is to its own cluster compared to others. A higher silhouette score means better clustering. So you want to pick K where the silhouette score is highest. Together, these plots help guide the decision, but always combine them with domain knowledge when possible. Now let's see some examples where we can use k-means clustering. In business, k-means is widely used to segment customers. You can group customers based on how often they buy, how much they spend, and what products they prefer. This helps businesses personalize offers and marketing strategies. In transportation engineering, maintaining the health of critical infrastructure like bridges, highways, and pavements is essential. By installing sensors that continuously record strains, vibrations, and displacements, engineers can collect huge amounts of data over time. Using k-means clustering, we can group normal behavior patterns separately from abnormal or suspicious behavior. A sudden shift of sensor readings into a new cluster might indicate emerging cracks, corrosion, settlement, or load issues, allowing for early repairs before catastrophic failures. Some other quick real-world examples could be like detecting early cracking in concrete bridges by clustering strain gauge data, identifying settlement or tilting in highway pavements from displacement sensors, monitoring dynamic loading effects on long-span bridges after earthquakes or storms. So k-means is great for many tasks because it's fast and easy to understand. However, it assumes clusters are roughly spherical and of similar size. It's also sensitive to the initial placement of centroids and requires choosing K before clustering begins. In summary, k-means clustering is a powerful tool for uncovering a structure in unlabeled data. It's efficient and widely used across industries, but it is important to be aware of its assumptions and limitations when applying it.